I'm going to preface this video by saying the universe is a very weird place for us simple mortals. Our lifespans are just a blink of an eye compared to the age of the universe, and things we expect to be constant like space and time behave very differently from what you may initially expect. So keep this in mind throughout the video. To answer the question of where the Big Bang originated, I'm going to have to provide some context. The leading theory regarding the beginning of the universe is the Big Bang theory, and without going into all the complicated details, I'll summarize it like this. About 13.7 billion years ago, everything that is in the universe today was crammed together into a space the effective size of zero. At the very beginning, not even atoms existed. It was just a hot and dense soup of fundamental particles. Since the beginning, the universe has expanded rapidly. As it expanded and cooled, atoms formed and stars were born. Now, the universe's expansion combined with the constant speed of light has turned the universe into a time machine. If we look at any region of space, we don't see galaxies as they are, but as they were. Galaxies we see in the foreground are much more developed, forming the more elegant and defined shapes you see here. That is because we are seeing these galaxies as they were only millions of years ago. They've had billions of years to form since the start of the universe, and so they look much more mature and developed. On the other hand, as we look at more and more distant galaxies, these galaxies appear younger. Galaxies that are billions of light years away appear as they would have shortly after the Big Bang, because the light emitted by them has taken that long to get to us. They look misshapen, and there is a lot of star formation going on within them, but in reality, it's important to remember that these galaxies are just as old as ours, and they no longer occupy the location where we can see them. They are probably much further away now, because of the expansion of the universe. It is also important to realize that there is no center of the universe, or conversely, that everywhere is the center of the universe, because it doesn't matter where you are, here or a billion light years away, everything is expanding away from you. Everything is expanding away from everything. Just as a side note though, gravity combats the effects of the universe expanding. That's why superclusters of galaxies exist, and the universe has a filamentary structure. The gravity from galaxies is attempting to keep clumps of them together, even though the expansion of the universe is also pulling them apart. What you end up with are filaments with empty bubbles or voids in between that will only get bigger as the universe expands further. You may have heard of the term the Hubble constant. This is how fast the universe is expanding, currently thought to be around 80,000 kilometers per hour per million light-year. So for a section of space 1 million light-years across, it expands by 80,000 kilometers every hour. A section 100 million light-years across would expand by 8 million kilometers every hour. The current value of Hubble's constant implies that the entire universe is expanding faster than the speed of light, meaning there is a sphere around us that we will not be able to see beyond. Past this sphere, galaxies are moving away from us faster than the speed of light, meaning light emitted by them can never reach us. Everything within this sphere is the observable universe, another term you've probably heard before. We can't see or detect anything beyond the observable universe, which is why we don't know if the universe is infinite or finite. Even if it is finite, it couldn't have an edge and would have to loop around because, well, the universe is just that, everything that exists. What would be beyond the edge of the universe otherwise? So we want to know where the Big Bang originated. Where in the night sky do astronomers look to see where the universe started? Well, the answer is everywhere because the universe always has been the whole universe. It has just changed in size from being very small to very big. It doesn't have specific coordinates because it is an explosion of the coordinate system itself. And this is what shortly after the Big Bang looked like, albeit in microwaves. This is what we call cosmic microwave background radiation, and you can see it anywhere you look into space, assuming you have a space telescope that can detect microwaves, because Earth's atmosphere is really good at blocking microwave radiation. 350,000 years after the Big Bang, the universe was hot, around 2,500 degrees. Even though this heat would have emitted visible light, we can't see it because the expansion of the universe has stretched the wavelengths of electromagnetic radiation by a factor of 1,000, meaning the photons no longer arrive at Earth as visible light, but rather as microwaves. So just like seeing those distant galaxies billions of light years away using visible light, we can see what the universe looked like before galaxies even existed by observing these microwaves. This makes this image effectively the oldest thing we have ever seen. Fascinatingly, the slight variations in the image are the precursors to the filamentary structure of the universe you've seen earlier in the video. We are quite lucky in that there are not really any bright sources of microwaves in the universe apart from the cosmic microwave background radiation, which means this view is a relatively uncontaminated view of the universe 350,000 years after the Big Bang. Can we see beyond that? No, not really. Before that, atoms were just becoming a thing and light couldn't travel through the soup of fundamental particles. So the center of the universe is everywhere and nowhere in particular. Look at any part of space with a microwave telescope and you're effectively looking at shortly after the Big Bang. Like I said, the universe is weird. You have probably heard that modern-day science believes the universe to be 13.8 billion years old. It seems rather unfathomable how anyone can come to that conclusion, but actually the how is not too difficult to understand. People just don't generally ask the question. Either they scoff at it or they accept it as truth. In this video we will explore this how, but also throw a spanner in the works due to the newly discovered age of one of our local stars called the Methuselah star, which apparently is older than the age of the universe, so 13.8 billion years old. How did we come to that figure? We currently see the universe is expanding and cooling. Everything is moving away from everything, excluding forces like gravity keeping things together. The speed of this expansion is known as the Hubble constant, and currently the universe is expanding at a rate of 80,000 kilometers per hour per million light-year. So the obvious conclusion from an expanding universe is that matter is becoming diluted. There's more space in between things. A less obvious result of the universe expanding is the stretching of light wavelengths known as redshift. What started off as extremely high energy and high frequency waves emitted soon after the Big Bang have become stretched, finally reaching us as less energetic microwaves known as the cosmic microwave background radiation. It's also why the James Webb Space Telescope is an infrared telescope, as photons of light emitted by galaxies billions of light-years away have had their frequency shifted to the red so much that we need an infrared telescope to observe them. A photon contains energy, and a higher frequency wavelength means more energy, which means it is hotter. Lower frequencies mean it is less hot. Hence why we say the universe was once dense and hot, but now it's bigger, but cooler. But how does knowing this help us work out the age of the universe? Well, we do need to assume a few things about the universe. First one, the universe is uniformly dense on the largest scales. This seems wrong. It's clearly not uniform. There are superclusters full of densely packed galaxies and supervoids containing not much at all. However, like stars in a galaxy, zoom out far enough and suddenly everywhere looks the same. So we assume the universe is homogeneous. As a result of that, not only is matter distributed evenly, but two, we also assume the universe's laws and properties are the same throughout in any direction, and three, we assume the Big Bang occurred in all locations everywhere at once. If you hadn't heard that before, you can check out my video about it here. Under the laws of general relativity, if these three things are true, then there is a connection between how old the universe is and how it expanded throughout its history. With these assumptions, we can get distance and brightness measurements between objects like stars, supernovae, and galaxies. For instance, white dwarf supernovae always appear about the same brightness. If an observed supernova is dim compared to what we expect, it is because it is further away. Finding out how dim tells us how far away it is, and thus, how far back in time we are looking. We can also look for fluctuations in the cosmic microwave background radiation, which is a snapshot of the universe only a few 100 million years after the Big Bang. Comparing it to galaxy clusters we see today, there is a correlation, so we can see how it's fluctuated to understand how the universe evolved and expanded. Based on the expansion of the universe today and how it did expand, we now know the universe is 68% dark energy, 27% dark matter, and 5% observable matter. But what is dark matter and dark energy? We really don't have much of an idea, however we can see their effects. Dark energy is believed to be the driving force behind the universe's expansion, as the expansion would have slowed down by now without it, and dark matter is gravitational force we can't account for. Galaxies and galaxy clusters in particular seem to have a lot more mass than they should, meaning the gravitational pull is stronger. Dark matter is what must keep galaxy filaments together. We can observe its influence. In fact, we can even map out its mass distribution like in this image, but we don't know what it is, we can't observe it. But for the purposes of this video we don't need to know what it is, only what it does to be able to work out the universe's age. So we know the current rate of the universe's expansion, or the Hubble constant, we know how that redshifts light, we know the composition of the universe and we know its properties. We can see how galaxies have evolved over time, we look for fluctuations in the cosmic microwave background radiation. We can use all of this together to extrapolate back to the earliest stages of the Big Bang. Using 3 different instruments all looking at different aspects of the universe, all the answers have come back roughly the same, 13.8 billion years with an estimated 99% accuracy. But there's another method which has thrown a bit of a spanner in the works, and that is to measure the age of stars. Certain types of stars are very short-lived, going supernova in a matter of a few million years. Others could last for trillions of years, not that we've seen one that old for obvious reasons. In fact, following the evolution of stars we haven't really seen any older than about 13.2 billion years old. But this does mean that long-lived stars that formed as matter was coalescing shortly after the Big Bang would certainly still be around today. And this is where our friend Methuselah comes in. Methuselah is a metal-poor star, meaning it is very old and incredibly rare. And most special of all, it is only about 200 light-years away from us, which means we can examine it relatively closely. Based on its evolution, it is an estimated 14.5 billion years old, give or take about 800 million years. This means it might have disproved the 13.8 billion figure. So do we really know how old the universe is? Roughly, it wouldn't be surprising to see this figure change as our technology improves. We have the WFIRST and James Webb Space Telescopes coming out soon with specific mission objectives to peer deep into the universe's past. Exciting times. Although I don't think we'll see this figure vary by more than about 1 billion years in either direction. Research is still in very early days in this field, even if it has been a topic of research for a while. To be honest though, I'm so impressed we have got this far. Who would have even thought we could come up with any figure a few hundred years ago? All this may throw up more questions than it answered, but that is science in a nutshell, the ongoing search for truth.